Hello everybody, I am Dr. Punyadarshini Poonam Tripathi from Agricultural and Food Engineering Department, IIT Kharagpur. Today we will be discussing about module 2, which deals with the performance analysis and computational modeling of solar drying systems. In my previous lecture, I have elaborated on the application of renewable energy for food processing and preservation, where we had given importance on the application of solar energy for food drying systems. And today we will extend the energy and exergy analysis of solar dryers part. So, these are some of the references which has been collected from books, journals and some web references also that is included here. Now, coming to the drying process, as we know that it is very energy intensive operation, and basically this is employed for preservation of fruits, vegetables and other agricultural commodities. The major processes involved in drying, basically it deals with the heat transfer and the mass transfer phenomenon, because it is a complex process of heat and mass transfer, where heat transfer takes place from surrounding heating medium or heating source to the product surface, and again from the product surface by conduction to the product surface, the mode of heat transfer is by convection, and from the surface to the inside of the food matrix by conduction heat transfer, the product is getting heated off, which in turn releases the moisture. So, moisture transfer from the interior of the food matrix to the surface of the food is due to diffusion, and again from the food surface to the surrounding air is by convective mass transfer. So, this simultaneous process of heat and mass transfer basically affects the end product quality. So, food drying, the basic importance of food drying is to achieve better quality end products, and at the same time the energy efficiency point of view we have to look into the process also. So, the ultimate aim of food quality in terms of color, texture, nutrient retention in the dried food material is going to enhance the market value of the food, consumers acceptability, and ultimately it helps in getting better profit for the dried products. So, in that regard, food drying not only includes the quality aspects, but at the same time being a highly energy intensive operation, we should look into the energy efficient drying processes by employing renewable energy sources. So, here I will be focusing on the energy and exergy analysis of solar dryers. So, since considerable amount of energy is required to heat the drying air so as to vaporize the internal water. So, here basically as we can see, very important part of energy analysis is to quantify the energy that is required for removing a certain amount of moisture from the food matrix, and to locate the exergy losses in each step of the drying process. Exergy is basically a thermodynamic process, and the details of energy analysis and exergy analysis we will be looking in the subsequent slides. Now, coming to the energy balance in solar dryers, in the previous class we have discussed about 3 common designs of solar dryers, namely direct, indirect and mixed mode type solar dryer. So, mixed mode type solar dryer being effective in terms of achieving faster drying rate and takes very less drying time as compared to direct and indirect, we will be analyzing the energy balance in the natural convection mixed mode solar dryer. So, as we know that this mixed mode solar dryer basically composed of a solar flat plate collector as well as a drying chamber. So, ambient air enters the collector, and as it passes across the passage length of the collector, the air gets heated off, and that hot air is entering into the drying chamber in order to remove the moisture from the food stock. So, here a number of energy equations can be derived based on the different components of the solar dryer. So, first part of the solar dryer is the solar collector, where we can see the bottom part is already known as the absorber plate, we already have discussed, and here due to convection there is convective heat transfer from the absorber plate to the moving air, and at the top of the collector we have a glass chamber, basically a glass cover we call it as, and solar radiation is directly falling on the glass cover. A part of it is absorbed by the glass cover, whereas the rest is reflected back to the atmosphere, and the rest part is transmitted through the glass cover and falls on the absorber plate. So, when the air passes over the absorber plate, the air is getting heated up and hot air enters the drying chamber. So, the different types of heat transfer mechanism that involves in the process of heat transfer in this collector part are HCPG, that is convective heat transfer from the absorber plate to the glass cover, HCAG, convective heat transfer from the air to the glass cover, HCPA, that is basically convective heat transfer coefficient from the plate to the moving air. There is convective as well as radiative heat losses that takes place from the plate to the cover glass, and similar phenomenon also occurs inside the drying chamber. So, to better understand the performance of the solar dryers, the energy balance equations at different components of the dryer has to be taken care of. So, here for a flat plate collector, we have deduced the energy balance here. So, as can be seen, the solar radiation intensity that is falling on the glass cover is designated as I. The solar radiation falling upon the glass cover is considered to be as I, that is the global solar radiation that is falling on the surface of the glass. Now, a part of that radiation is reflected back to the atmosphere, and the energy gained by the glass cover is designated as Ig, which is alpha j into I, that is a portion of the radiation absorbed by the glass cover. Alpha is the absorptivity of the glass cover and I stands for the radiation intensity that is falling on the glass cover. So, the rest portion is transmitted and is falling on the absorber plate. So, the solar radiation absorbed by the absorber plate is given by capital S, where we can write S as transmittivity of the glass cover, absorptivity of the plate, that is the absorber plate, and the solar radiation intensity. Here the nomenclatures are also provided. So, S is the solar radiation absorbed by the absorber plate, and there are some amount of heat losses also to the ground, that is bottom loss, which I have already discussed in my previous lecture. Bottom loss, there is top loss, and also there are side losses. So, the useful energy that is available from the collector to do some work is designated as Q. So, the energy balance of the different components we are expressing here. So, the energy balance equation for the glass cover is expressed as the energy absorbed by the glass cover, that means energy gained by the glass, and the energy lost through the glass. So, the energy balance of the glass cover is expressed as alpha g into I, where alpha g into I we have already mentioned as the energy gained by the glass cover, plus HCPG plus HRPG. HCPG is the convective heat transfer from the plate to the glass cover, because absorber plate also have some heat losses to the top cover. So, that is designated as HCPG, convective heat transfer coefficient from the absorber plate to the glass cover. So, heat loss from the absorber plate is automatically the heat gained by the glass cover. Similarly, HRPG, that is the radiative heat loss from the absorber plate to the glass cover into the temperature difference between the plate as well as between the glass cover, the temperature difference between the plate and the glass cover, that is nothing but equal to HW is the wind heat transfer coefficient basically, that is the outward heat loss from the cover glass to the surrounding, HRGS radiative heat transfer from the glass to the sky, and the temperature difference between the glass and the ambient air. This is the energy balance for the glass cover. Similarly, coming to the energy balance for the absorber plate, the energy absorbed by the absorber plate, which already I have shown, that is designated as S. This is the energy absorbed by the, or the radiation basically absorbed by the absorber plate. So, S is nothing but equal to HCPG, convective heat transfer coefficient from the plate to the glass cover, plus radiative heat transfer from the plate to the glass cover into the temperature difference between the plate and the glass cover, plus this is the radiative heat transfer coefficient between the plate and the bottom bottom plate basically. So, because this is the bottom plate, so and I have mentioned there is heat loss to the bottom. So, this can be represented in terms of energy balance equations for the observer plate, where HRPB represents the convective heat transfer coefficient between the plate and the bottom plate. This is the observer plate, and B is the bottom insulation part, that plate, how much heat is being lost, into plate temperature minus bottom temperature, plus there is convective heat transfer coefficient between the observer plate and the fluid. Here fluid we are assuming as air. So, there will be convective heat transfer from the plate to the fluid multiplied with the temperature difference between the plate and the fluid. So, the useful heat gained by the fluid, because whatever amount of energy is being absorbed by the air, that is going to help in doing some useful work. As can be shown over here, Q is the useful energy gained by the fluid. So, useful heat energy gained by the fluid is nothing but equal to the heat gained by the fluid from the observer plate by convection. So, Qu is the useful energy gain is nothing but equal to mCpdT. This is mass flow rate of air into Cp specific heat. T naught is the collector outlet temperature and Ti is the collector inlet temperature. That is nothing but equal to the convective heat transfer coefficient between the plate and the fluid into Tp minus Tf, plate temperature and fluid temperature. This Tf, that is the fluid temperature, can be calculated as the average of inlet and outlet collector temperatures. Ti is the inlet collector temperature, To is the temperature of the fluid at the collector outlet. So, the average of these temperatures is designated as the fluid temperature, and normally in experimental practice different thermocouples are being placed. As can be seen, these red color marks are the position of the thermocouples are placed at different locations of the collector as well as the drying chamber, so that effective temperature measurements at any instant during the test period can be monitored, and those temperature parameters are used for developing the energy balance equations, which gives us an idea about the performance of the solar dryers, and this performance can be expressed in terms of efficiency, that is thermal efficiency of the collector, as well as the convective heat transfer coefficient from the bottom plate or the observer plate to the moving air, because higher will be the convective heat transfer coefficient, higher will be the drying rate. So, our objective is to enhance the heat transfer coefficient and at the same time the thermal efficiency of the collector. So, in this regard, the convective heat transfer coefficient between the observer plate and glass cover, that is HCPG, for natural convection condition is also represented as the given expression. HCPG is nothing but equal to Nusselt number into thermal conductivity of air upon the distance between the plate and the glass cover. So, K air is the thermal conductivity of the fluid, and Hc basically is represented as the distance between the observer plate and the glass cover. Nusselt number here for between the plate and the glass cover is designated by this empirical correlation, where this equation is valid for angle theta ranging between 0 to 75 degree, where theta is the inclination angle of the collector, and that basically depends on the latitude of the place where the system is installed. This positive sign, as can be seen from this equation, the square brackets, you can see these positive signs. This positive sign represents the implication that only positive values of the terms in the square brackets are to be considered for calculation of Nusselt number between plate to the glass cover. Now, coming to the Rayleigh number, which is one of the parameter in this expression. So, Rayleigh number can be calculated by this expression that is given as rho square Cpg beta Tp minus Tg Hcq upon K air into mu, where rho is the air density in kg per meter cube, Cp is the specific heat, G is the acceleration due to gravity, beta is basically the thermal expansion coefficient, and Hc we have already mentioned the distance between the observer plate and the glass cover, and mu is the dynamic viscosity of air in Pascal second. Now again the convective heat transfer coefficient between the observer plate and moving fluid, this is very important part which plays a huge role in deciding the drying rate of the food materials during the process of drying. So, this can be again correlated in terms of Nusselt number is nothing but equal to Hc. This is basically dH represents the hydraulic diameter. So, upon KAR. So, HCPF is nothing but equal to, from the previous correlation we can find this as mCp/dt upon temperature difference between the plate and the fluid, and dH is the hydraulic diameter, and for this solar flat plate collector it takes a value having the representation 4 SC upon P, where SC is the cross sectional area of the collector and P is the weighted perimeter of the collector air channel. So, analyzing these temperature variations at different locations of the collector, the thermal efficiency of the flat plate collector can be determined, and thermal efficiency is defined as the ratio of useful heat energy to the total solar energy incident on the solar collector at any given time. So, this thermal efficiency is represented as QU upon IAC, where I is the radiation intensity that is expressed in watt per meter square and SC is the collector area. QU is nothing but equal to mCp/dt, already we have seen it. So, the useful energy gain by the collector is nothing but the energy received by the collector minus the energy lost from the collector. So, here Fr is an important parameter to be incorporated to analyze the efficiency of the heat exchanger, and in this case this solar collector is the heat exchanger which plays a major role in performing some useful work. So, according to Hotel-Wheeler-Bliss equation, QU, that is the useful energy, is nothing but equal to, is given as QU is equal to Fr into I tau alpha into Sc minus UL into Sc into Ti minus Ta. This UL represents the overall heat loss coefficient which we have seen in the previous lecture, that takes care of top heat loss coefficient. UL is nothing but equal to top heat loss coefficient, bottom heat loss coefficient and edge heat loss coefficient. So, this UL into collector area into Ti is the inlet air temperature to the collector and A is the ambient temperature. So, from this QU efficiency can be calculated as a function of Fr tau alpha and Fr UL into Ti minus Ta upon radiation intensity, and if we plot the experimental data we can see the efficiency versus the temperature difference between Ti minus Ta upon I. So, here the intercept we are getting as Fr tau alpha and slope as Fr UL. So, Fr is known as the heat removal factor. So, this equation basically resembles the straight line plotted between this thermal efficiency and the temperature difference between inlet air and ambient temperature upon the radiation intensity. And Fr tau alpha is known as the absorbed energy parameter, how much energy is being absorbed by the collector. So, this Fr tau alpha, because tau alpha represents the product of transmittivity and absorptivity, and Fr UL is the removed energy parameter. So, considering the absorbed energy parameter and removed energy parameter from the collector, the efficiency has been calculated for the flat plate solar collector. So, based on the different energy balance equations, the performance parameters, one is the different temperature variations at different locations of the system that we have presented here for 3 different types of dryers, that is direct dryer, indirect and mixed mode solar dryer. And here as can be seen, the observer plate temperature, glass cover temperature and hot air temperature along with the solar radiation intensity are being plotted over here. The temperature data can be collected with the help of the thermocouples, whereas solar radiation intensity is measured experimentally with the help of a pyranometer. Similarly, this is for direct, indirect and mixed mode solar dryers we have shown, and it is observed that the air temperature achieved in case of direct type solar dryer is in the range of 52.9 degree centigrade, for indirect 47.3 degree centigrade and for mixed mode around 59.8 degree. So, here the air temperature is found to be maximum in case of mixed mode solar dryer, because mixed mode solar dryer is taking the advantage of heating the air through collector as well as the drying chamber, where the combination of direct and direct and indirect type solar dryer technology is being incorporated in mixed mode. So, higher or maximum temperature is achieved in the mixed mode solar dryer, because in case of indirect the top cover of the drying chamber is opaque. So, direct radiation is not falling. So, maximum temperature achieved is for mixed mode solar dryer. Similarly, the other performance parameters are the efficiency and the convective heat transfer coefficient. So, it was observed that the thermal efficiency was also maximum for mixed mode solar dryer, followed by direct and least for indirect solar dryer. And similarly, the heat transfer coefficient, convective heat transfer coefficient is maximum for mixed mode, having a value of 23.81 watt per meter square degree centigrade, followed by direct type and least for the indirect type solar dryer. But however, in all the three cases it was observed that the thermal efficiency as well as the HCPA, they continuously decreases throughout the test period, and the maximum value is obtained in both the cases for mixed mode solar dryer. Now, coming to the next part of the performance analysis, where we are dealing with the exergy analysis. Basically, we have seen energy balance at different components of the collector is very important in order to achieve the maximum drying rate, and these energy balance equations are done in order to, or derived in order to find out the performance. But energy basically provides no information about the quality or grade of energy crossing the thermal system boundary, and no information about the internal losses that are taking place. So, in this regard, the exergy of an energy form or a substance is a measure of its usefulness or quality or potential change. It is the energy available for specific work. Basically, it is a thermodynamic concept, and it is defined as the energy available for doing some specific work, and it denotes the maximum amount of work that can be performed by a system under steady state condition. Unlike energy, exergy is conserved only during ideal processes and destroyed due to irreversibility in real processes. What does mean by irreversibility? For example, suppose heat transfer is taking place from a body having higher temperature to a body having lower temperature. So, here it was observed that the temperature of the destination or the temperature of the body where heat is being transferred is not the same as that of the source, because there is some amount of heat loss or energy loss during the transformation or during the conversion from a higher temperature to a lower temperature. So, this energy loss basically is represented or expressed in terms of entropy generation. So, as a result of entropy generation, the quality of energy is basically degraded from the source to the sink. So, this degradation of energy is basically known as the exergy loss or irreversibility in the system. Exergy analysis therefore has an important role in designing assessment, optimization and improvement of the energy systems. In that regard, the need of analysis can be used to determine the type, location and magnitude of energy losses in a particular system, and it can be used to reduce losses to make the system more efficient. Now, coming to the exergy analysis of solar dryers, as we can see, this is the inlet to the collector where exergy in is represented over here, and there are exergy destruction due to irreversible heat transfer process, as I have discussed right now how the exergy is being lost or destructed due to irreversible heat transfer. Okay. Similarly, this is exergy losses due to heat losses from the collector, and in order to get into the details of this process of exergy analysis, so exergy of a solar collector is defined as the maximum amount of work that can be produced by a solar collector before reaching equilibrium with a reference environment. And an exergy balance in the solar collector can be defined as the exergy in, that is basically the summation of exergy in into the system minus summation of exergy out from the system is nothing but equal to the exergy that is destructed inside the system. So, what is the exergy in? This is the exergy in due to radiation intensity and due to the fluid that is entering into the system, and exergy out is the outlet exergy from the system. So, exergy of working fluid, that is given as mCp into temperature difference between the fluid and the air, ambient air, minus Ta into ln Tf by Ta, where exergy rate at collector inlet is designated as Ex in, which we have already shown over here. Ex in, this is the exergy rate at collector inlet, and exergy of the input fluid is Exf in. This is basically exergy of input fluid. Exergy fluid inlet is nothing but equal to mCp into fluid inlet temperature minus ambient air temperature minus ambient air temperature into ln of T fluid in upon Ta. Similarly, exergy of outlet fluid is Exf out, that is mCp fluid out temperature, or this is the temperature of the outlet fluid minus ambient air temperature minus Ta into ln of Tf out upon Ta. So, what is the exergy gained by the fluid? This is exergy out minus the exergy in. So, the exergetic efficiency of collector can be defined as the ratio of the output energy to exergy inflow to the collector. So, exergetic efficiency is designated mathematically as exergy gain upon the exergy input to the system. Similarly, exergy balance for the drying section we can see over here. Exergy input to drying section basically designated as EXD, D for drying section or the drying chamber. So, exergy inlet to the drying chamber is the exergy outlet from the collector plus exergy due to radiation intensity, because in the drying chamber the air that is moving into the chamber is coming out from the collector outlet. So, there is some exergy from the collector outlet that should be the input to the drying chamber. So, associated energy losses in the drying chamber deals with the exergy loss with the air leaving the dryer, exergy losses from the walls of the dryer and exergy loss in the product. However, the exergy loss in the food material or the product is very negligible. So, that is not taken into consideration here. So, the rate of exergy of input fluid to the drying chamber again can be represented in the same form as we have done for collector part. So, exergy of the fluid that is moving into the drying chamber is nothing but equal to represented as mCp T drying chamber temperature at the inlet minus ambient air temperature minus Ta ln of Td in by Ta, and the rate of exergy of fluid going out from the drying chamber is designated as exergy out from the drying chamber is equal to mCp into temperature of the drying chamber at the outlet minus ambient air temperature minus Ta ln of Td out by Ta. So, the difference in the flow of exergy between the inlet and outlet of the drying chamber is equal to the sum of the thermal exergy loss and the exergy destroyed due to irreversibility. So, exergy destructed or loss inside the drying chamber can be represented as summation of exergy into the drying chamber minus summation of exergy out from the drying chamber is summation of exergy destruction inside the drying chamber. So, exergy efficiency of the drying chamber is defined as the ratio of the exergy outflow to the exergy inflow inside the drying chamber, and accordingly the exergetic efficiency for the drying chamber can be represented as exergy out from the drying chamber upon exergy in into the drying chamber. So, based on this exergy fundamentals, we will solve one numerical here. Calculate the exergy gain by the air as it enters the solar collector at 30 degree centigrade and comes out at 50 degree centigrade. Ambient temperature and mass flow rate of air are given as 25 degree centigrade and 0.2 kg per second. Specific heat of air at average collector temperature is given as 1007 kilojoule per kg Kelvin. So, here it is given that air temperature at the collector inlet is 30 degree centigrade and air outlet temperature at collector outlet is given as 50 degree centigrade. The ambient air temperature is 25 degree centigrade and mass flow rate of air is given as 0.2 kg per second, and specific heat is already given. So, in that case we have to find out what is the exergy gain by the air inside the collector. So, temperature of air at collector inlet is given 30 degree, which is 303.15 Kelvin. At the outlet we are getting 323.15 Kelvin, and ambient air temperature is 25 degree centigrade, which is 298.15 Kelvin. So, exergy of the fluid at the inlet section is represented by the mathematical expression which we have seen previously for the collector system. Exergy of the fluid at the inlet is nothing but equal to mCp dt, mass flow rate of air, Cp is given, dt is the fluid inlet temperature minus the ambient air temperature minus ambient air temperature into ln of fluid inlet temperature upon the ambient air temperature, and we are getting as 10.07 watt for the exergy input into for the exergy of the fluid at the inlet section. Similarly, exergy of the fluid at the outlet section can also be found out in the same way, mCp dt. This is the temperature of air at the collector outlet, ambient air temperature, again Ta into ln of Tf out, that is 323.15 upon ambient air temperature, and exergy of the fluid at the outlet section of the collector is calculated as 199.98 watt. So, exergy gain by the fluid will be exergy of the fluid at the collector outlet minus exergy of the fluid at the collector inlet section. So, that is nothing but equal to 199.98 minus 10.07 is 189.91 watt. So, today we will stop here and next we will proceed further. Thank you.